Hi, this is my lab for tidal circuits. The purpose of this lab is to predict the behavior of circuits with resistors in a series and in parallel, use multimeters to measure the value of conventional current and potential differences in the circuit, and observe the behavior of ohmic resistors and capacitors. In our findings, we saw that the current and voltage values given by the model matched the predicted values in most of our experiment, and that the RC experimental value was 6.035 seconds compared to the RC true value of 6 seconds. Here's some of the concepts that I use for the lab. Loop rule is an equation that states the sum of all the electric potential differences around a loop is equal to zero. The node rule, also known as the conservation of current, states that the sum of current flowing into the node is equal to the sum of current flowing out the node, as shown by the equation here. And Ohm's law is a formula that is used to calculate the relationship between voltage, current, and resistance in an electric circuit. This equation states that the voltage across a conductor is directly proportional to the current flowing through it. Resistor equivalence is the equation for the total electric resistance caused by all of the resistors in a circuit acting together against the voltage source. And there are two different equations for the in-series and in-parallel circuits. Capacitance is the equation for the ratio of the change in the electric charge of the system to the corresponding change in the electric potential. In the first part of the experiment, I predicted the current through a separate circuit using the loop rule with the given information below. In my calculated prediction, I first used the equation for resistance in a series to add up the total resistors in the circuit. It got 147 ohms, and then using Ohm law, rearranged the equation to solve for the current, in which I got a value of 0.02 amps. Testing from prediction was correct. I actually created a model of the simple circuit shown in the previous slide and found that the ammeter prediction was actually correct and ended up being 0.02 amps. When I reversed the connection of one of the ammeters, the same results were produced and I got a current of 0.02 amps. I then replaced one of the ammeters with a voltmeter to see the effects of the current and saw that the voltmeter read 3 volts because the black probe is connected to the battery and that the ammeter read 0 amps because the circuit is open. And here you see two pictures of both circuits. Here, I used the voltmeter to measure the potential differences between each of the points listed in the diagram. For most of the points, I got a potential difference of 0 volts, but for the potential difference of the battery, I got a value of 3 volts. For the potential difference of the 47 ohm resistor, I got a value of negative 0.96 volts. And for the potential difference over the 100 ohm resistor, I got a value of negative 2.04 volts. We can tell that this satisfies loop rule because the sum of all the potential differences is 0. Here's a graph of the potential differences from the previous slide. As expected, the start and ending potential difference is 0. When you attach the voltmeter, the ammeter reading does not change because the voltmeter has a very high resistance, so very little current flows through it. Because of this, the ammeter barely changes when the voltmeter is attached to the circuit. Now, when the parallel emitter circuit is created, the current gets split between two paths. Since the emitter has an extremely low resistance of almost 0 ohms, all the current will avoid the 100 ohm resistor and create a higher current. This will overall lower the total resistance of the circuit from 147 ohms to 47 ohms. This is shown in the diagram in which our new current is 0.06 amps. We can use our measurements from part 5 and 6 to calculate the resistance for each of the following circuit elements. Notice that the R wire and the R emitter have 0 ohms for the resistance. In this part of the experiment, we used the 10 ohm bulb and 20 ohm bulb to create an RC circuit and created two scenarios in which the bulb is connected in series to the battery capacitor and the bulb is connected in series to just the capacitor. We saw that in both scenarios that the light bulb became very bright and dimmed off until the light turned off, and the current started large and slowly decreased until it became 0 amps. Then we calculated the time for the capacitor to charge and discharge for both the 10 ohm bulb and the 20 ohm bulb, and saw that for both scenarios, the time the capacitor was almost the same and it increased as expected when we went to the 20 ohm bulb. Here we have a setup similar to the previous section in which we have a 9-volt battery, 0.2F capacitor, and a 30 ohm bulb all connected in series. In this part of the experiment, I created a circuit, got my stopwatch, turned on the circuit, and then paused the stopwatch for every second interval to record the potential difference for 20 seconds. As time passed, the potential difference will decrease each second. I then created a table for the time, potential difference, and the natural logarithmic expression for the potential difference over the initial potential difference, which was 9 volts. It plotted the table below. Then we will use the table to plot our graph and determine the slope of our expression. Here's a plot of the ln(v) over VL versus time table from the previous slide. See, here we use the slope of -0.1657 to calculate the experiment RC by rearranging the equation and solving for the RC experimental variable, which is 6.035 seconds. Compared to the RC value, which is 6 seconds, we found a percent error of almost 0.58%, which is very small. Here are some possible errors that could have occurred with an experiment. There could have been error with the voltage measured in the circuit, which could be solved by performing multiple trials to make sure the voltage is accurate as possible. There could be error due to routing calculation, which could be solved by keeping calculations as is throughout the experiment. And there may have been human error in stopping the stopwatch, which can be solved by using a code or program that can stop and record the voltage at each second interval. If a real alternator was used in a lab, because a real alternator does not have zero resistance, when the alternator is connected to the resistor in a parallel circuit, some of the current would have gone to the resistor. In the virtual experiment, however, since the emitter resistance was zero, none of the current went through the resistor. If a real battery was used to charge a real capacitor with no resistor in the circuit, our model predict that the capacitor will charge instantly. If there was no resistor in the real life circuit, since batteries actually have a turnaround resistance, the capacitor would not actually charge instantly.